Thanks. So my name's Andrew Wellington. I'm the Senior HPC Systems Administrator at NCI in Australia. So what I'm going to talk about basically what is NCI, because I'm sure most of you have never heard of us. The past, to give you a bit of context of where NCI has come from and where some of our ideas of what on earth we're doing has come from. The present, so what we're actually doing today, then we'll move into the future. What are we looking at in the relatively near future? What questions have we got? And then we'll have some questions from you guys. So what is NCI? Well, NCI is Australia's national high-performance computing service. So we provide comprehensive computational research services to a number of organisations around the country. We provide national access, so any researcher at an Australian university can apply on the basis of merit through our merit allocation scheme. That's then assessed by a committee of academics who decide on the merit of any of the proposals. And we're quite driven by research objectives, so we're not just buying a computer because, hey, everyone wants a supercomputer. We care about what research is actually done. The NCI actually operates as a formal collaboration between the ANU, so the Australian National University, the CSIRO, that's the Commonwealth Scientific and Industrial Research Organisation. You might know them from suing companies over Wi-Fi patents. They invented Wi-Fi basically and wanted some money out of it. They did actually win most of those. The Australian Bureau of Meteorology, so they use NCI to develop their weather modelling, sort of the next generation before they run them in production. And Geoscience Australia, so the governmental geoscience organisation. We're also a partnership then with a number of research-intensive universities around the country, so they also buy shares of the machine, essentially. So where are we located? We're in the nation's capital, so there's Australia, a very long way from here. In Canberra. So national capital of Australia is Canberra. It's not Sydney, as most people believe. It was a planned capital, so basically Sydney and Melbourne both wanted to be at Federation, and we said, nah, neither of you can be, and built a new city for it. We're at the National University, so the Australian National University there. So what do we research? Focus areas for our research? Well, the current machine was essentially built as a climate systems and earth systems science machine. So that's where a lot of our stuff came from, the Bureau of Meteorology and CSIRO doing a lot of work in that area, and some of the other universities, so the University of New South Wales, that sort of thing. We also do a lot of work in astronomy, geoscience, biosciences, computational sciences, social sciences, and with a growing emphasis on data-intensive compute. So we've got a lot of people now with huge data sets that they want to work on, and they need somewhere to have the data and then actually compute on it. So we've got a couple of the things up there of some of our sort of pretty brag wall that we have in the boardroom. So we've got everything from really theoretical pure science, the greatest map ever, that's SkyMapper, which is a most comprehensive survey of the Southern Hemisphere's night sky, being led by Brian Schmidt, a Nobel Prize winner at the university. We've got other things like we've got more of the climate research there as well. So who uses NCI? We've got around about 3,000 plus users, about 10 new users every week, constantly growing. And there's around about 600 active projects at any one time. So those projects cover the whole gamut of research there, from astrophysics, biology, climate, mathematics, pure mathematics, image processing, geophysics. Essentially, if it's computational research, we do it. So this is just the general graph of well, what are they actually using it for? What jobs are we seeing come through? So that really big blue chunk is Earth Sciences. So that includes your climate and weather stuff. So that's the largest part at the moment. But then we go into physical sciences, chemistry, engineering, biology, everything you'd expect. So, to come through some of our past machines, to give you an idea, this is the machines of around about the last 15 years, more accurately the ones that I could find pictures of. So here we've got SC. I believe SC stood for supercomputer, very imaginative at the time. Had 126 nodes with 4 processors each, so 504 CPUs in that machine. Theoretical peak of just over 1 teraflop, and LinPacked at around 820 gigaflops with a Quadrix interconnect there. So then, at the same time, we sort of had a lot of these smaller jobs that people wanted to run, single node jobs, which was not a great fit for a big, expensive machine, so we built Linux cluster. You can see it's a bunch of Dell desktops sitting on some shelving at the end of the data center. It had its own theoretical peak of over 800 gigaflops, but it only had gigabit Ethernet interconnect and a gig of RAM per node, but it worked really well for some of those sorts of jobs. So then we had AC. It's a lovely SGI machine you can see there with Itanium 2 processors, going to be the future. Around about 2,000 cores there. And of course, because it was one of these machines that you could actually move things around, we ran it in about 30 partitions of 64 processors each. That did change over time. Once again, a theoretical peak of around 11 teraflops there. XE. So this guy also ran kind of simultaneously with AC and our next machine. And was our first machine with GPUs in it at all. This one, same sort of idea. It's about 1,200 cores, about 15 teraflops, and it was our first machine with InfiniBand interconnect, DDR, and the same there. We had 32 GPUs. Interestingly, none of our machines since then have actually had GPUs, but we're looking at them once again. And this is our immediate previous machine to the current one, Vayu, the Hindu god of wind, I believe. It was around 1,400 nodes, and we'd moved up to sort of 12,000 cores, theoretical peak of around 140 teraflops with QDR InfiniBand. That's a Sun machine. We bought it from Sun. About a month or two later, they were bought by Oracle and stopped doing any HPC stuff. Good timing there. And now our current peak HPC machine here, this is Raijin. It's a Fujitsu machine with 3,592 nodes, each with 2 8-core Sandy Bridge processors, so 57,500 cores. Theoretical peak of about 1.2 petaflops. The first petaflop machine in the Southern Hemisphere. FDR InfiniBand interconnect, it's a full fat tree, and has around 52 kilometres, 32 miles for Americans who don't understand kilometres and metric, of InfiniBand cabling. Uses around about a peak of 1.5 megawatts of power. And it also has access to our global Lustre file systems. So these are ones we store data sets on and are not directly part of our HPC machines. And it's also used then by things like our cloud. So this is a true high-performance cloud. You go out to Amazon or other people, you get a cloud, it's a bit rubbish. It's got gigabit interconnect, maybe 10 gig if you're lucky. This guy has a full FDR fat tree behind it. So it's still providing cloud, so it runs through OpenStack, but this is high performance. We can easily beat any benchmarks we've ever done on Amazon AWS with this guy. And it also has access, once again, to our global Lustre file system. So you can sort of share data between them. You might use this for visualization or providing something in front of something that you've just done a lot of really big, heavy compute. So the past. Before Raijin, we used to run our own version of PBS. It was ANU PBS, a heavily customized fork of OpenPBS version 2.3. What did we do to it? Well, we went nuts. We had years working on this, so we added a bunch of new commands. We've got job nodes, jobs on node, it could tell you all that sort of stuff, things that you couldn't easily get out of the OpenPBS commands. We modified a number of commands. We wanted to add new options, added new stuff. Then we added a unique scheduling algorithm. I'll get to that in a second. We also then had very tight integration with our own locally developed accounting and allocation system. We connected it up to a licensed shadow daemon. So we've got a lot of licensed software running on the machine. We do prefer open source stuff because there's no licensing, but there's a lot of stuff that people need licensed software, and we've only got so many licenses to go around. So we need some way of tracking it and making sure that your job isn't going to run when it won't have a license available. We added support for a local JobFS file system. So that's a local Scratch file system you could use, and support for CPU sets so that we could make sure you've been allocated that CPU, you're not going to use any more than that. Let the kernel do the work for us, much easier than trying to do something yourself. We also had the concept of draining the system or individual nodes. So we had essentially the equivalent of dedicated time options, but we could have that for an individual node much more easily. And we could configure nodes to have a maximum wall time. So this node might only run jobs of a wall time of 2 hours. This was really, really useful when a node had failed. You've just brought it back into the cluster and you're sort of still a bit iffy about it. Is it going to work? People are a lot happier if their job's only 2 hours that fails because of an iffy node than a 2-week job failing because of it. So our accounting system, we tied in quite closely with RASH, the Resource Accounting Shell. It's another locally developed thing there. Did a lot of that then. And it allowed ANU PBS to make scheduling decisions based on accounting data, so deciding how much a particular project had used throughout the time, what it's used. This tight integration, though, meant it was really quite difficult to port RASH into PBS Pro, so we've actually got a new accounting system now. And this was the really cool part. It was a suspend resume-based scheduler. So the scheduler only thought in terms of suspend resume. It didn't think backfill, didn't think anything like that. It only thought, should I suspend a job to run this job, or should I carry on and we'll wait until we've got something available? So every job had the possibility to suspend, in theory, any other job. Not just express queue jobs, not just sort of soft limits, that sort of stuff. Any job could do that. The advantages of this, it was really good. Large parallel jobs didn't require reserved nodes to be available. It didn't require this sort of draining backfill available. Express queue jobs or debug jobs or interactive jobs didn't require reserved nodes. They could just jump in, suspend something, do your work, drop out. And those long-running jobs didn't prevent other jobs from running. That was very important. The disadvantages of it, if you don't manage it properly, you could end up with excessive paging, pushing stuff out to swap. Not good. HPC, swap don't mix very well. But for a suspended job, it's not too bad to push some of it out to disk and bring it back in. And too many suspended jobs with not enough new jobs sitting in the queue actually could end up leaving free nodes, which make you very sad. Fortunately, we don't usually have very many, any lack of jobs sitting in the queue. So in general, jobs in the same queue had the same priority. So our normal queue or our express queue, they all had the same priority. And it basically worked by doing a pairwise comparison of every job as a potential preemptor and preemptee. And it would consider many factors. This is just some of them. Relative wall times, the number of CPUs compared, already suspended time, existing resource usage by user and project, how close jobs are to completion. It's a huge list of factors. But today we're using PBS Pro. We're, as of today, using PBS Pro 12.0 based custom branch that Altair have developed for us, adding some features. It's using a backfill-based scheduler now, with some sort of the major points of customization have been our allocation and accounting system, AlecDB, priority calculation scripts around it to try and push up jobs that we like. So in general, the jobs that we like are lots of CPUs. We want you to use a nice big parallel job on our machine. Paid a lot of money for some InfiniBand, please use it. Single CPU jobs or single node jobs don't use that very well. We've also got limits on the running CPU memory wall time that an individual job can do. And we also support munge authentication rather than the weird low reserved port thing. This provides actual cryptographic proof that you really are who you say you are, not just trusting that, oh, you've got a low port number, you must be who you say you are. But why would we go to PBS Pro? What's wrong with us? Why would we move away from a PBS that we've been developing for years and go on to something like this? Well, during acceptance testing of Raijin, we were thinking we'll keep using a new PBS, hey, it's been going great. And then the lead developer left NCI. At the same time, actually, one of the other system administrators left, wasn't looking good. And PBS Pro offered a nice supported scheduler and resource manager that was going to be available to us. Altair offered to work with us to customize PBS Pro for our needs. It was something from the same heritage, so it's PBS-based. Users would understand QSub. You don't suddenly go to a competitor and go, well, what are all these commands? I don't understand them. And if we're going to do a change, it's probably the best time to do it when we're moving to a new machine and people are going to have to make some changes anyway. So we thought, PBS Pro, that's got suspend regime too. Why don't we use it there? Well, we looked at it and we found some issues. It's probably because of the way we try and suspend everything, support anything suspending, but we found issues like more CPUs being suspended than were required to run a job. Well, that's kind of stupid. Why am I doing that? There was less flexibility in selection of jobs to suspend. So the express queue kind of could suspend other things, but there was no way of forcing every job to be able to suspend other jobs without it working well. At one point, the scheduler was actually trying to suspend jobs, even when there were CPUs free to run the job. I don't know what was going on there. I haven't seen it since, so maybe it was just a one-off bug, but that was really bizarre. We had a number of free nodes, and it thought, I'm going to suspend those anyway. And the worst part is that a job can actually end up suspended forever, just about. Their node keeps getting selected to run other jobs because it was a low priority job, and their job just sort of sits there, dying a slow death. But what we've found is that really PBS Pro's suspend regime works brilliantly for high priority express kind of jobs, not so great to try and implement our previous algorithms. So this gives you an idea of, this was a bunch of sample jobs run through our test cluster based on a day of real jobs out of the real cluster, for me to try and test, well, what's going to happen if we do enable this full suspend regime with PBS Pro. A small number of jobs available as a preemption target meant that jobs are constantly being picked on by the scheduler. So you can see that jobs were suspended for easily 150% of their actual requested wall time. So they ended up asking for a couple of hours, so in this case I scaled them all down to 10% of their real sizes, so I didn't have to wait for weeks for the test to run through. PBS Simulator, Scheduler Simulator sounds awesome, I'd love that. And you can see that jobs actually ended up suspended for massively more than their actual requested wall time. Not great for us. So moving on to our accounting system that we use today. So NCI allocates compute hours to a project across a quarter, so over 3 months. And we allocate those based on individual stakeholders, so the Bureau of Meteorology or CSIRO pay for a portion of the machine. They get told, well, you've got this many hours you can allocate them however you like. Well, they allocate them to projects, and we need to account for that. So the system passes the accounting logs provided by PBS and gets further information from QStat-FX, the history of jobs that have run in the past 24 hours on our system. One thing we found is the accounting logs in 12.0 at least, I don't know if this is fixed in 13, don't include resource usage for jobs that get deleted due to a MOM going down. It just tells you that it was deleted due to the MOM going down, and we can't find out. Because we charge for time regardless of whether your job completed, You still use the time, we still charge for it. That was a bit of a problem for us, so we do use the QStat output to actually get that data. Another interesting factor of our machine is once a project is actually out of quota, we don't care. We still want to allow you to run jobs if there's no jobs for people who are in quota. So we call it bonus time, and we do get people running quite literally hundreds of thousands of hours of jobs in bonus. For us, that's really good. Spend a lot of money on a computer. I want to use every CPU hour that is available on that machine. The only other factor in our current accounting system is it's somewhat manual in some areas. So there's, particularly in reporting areas, there's some work needs to go in there. So we also integrated our custom license shadow daemon back into PBS Pro. So the LSD actually works by tracking the usage of licenses across a number of commercial packages. It has knowledge of the pattern of license usage that individual programs use. So this program happens to use 20 licenses when you run it on 20 nodes, and this one uses 4 licenses when you run it on 20 nodes for some reason, so it knows how that actually gets used. And jobs can request licenses where they'll be reserved by LSD and will hold back jobs that don't request, that can't run because they'll conflict with licenses that are already available. So we use hooks to integrate with PBS Pro to reject running jobs, a job that's about to run when licenses aren't free. It'll still stay at the top of the queue and will run essentially the moment those licenses are available. Another feature is we also detect rogue jobs that use licenses with no PBS request. So we'll send the user an email automatically and say, hey, you're using this program, you haven't requested it, so you probably need to include this line in your PBS job script to request it. If someone keeps doing that, eventually we'll hold all their jobs until they write back to us and say they'll be good and do what we tell them to. We also implemented local job affairs, once again with hooks. It's amazing what you can do with hooks. So we allow users to request temporary storage that's node local. It's handled with 3 different hooks there. So a run job hook, creating a temporary folder on that disk, periodic hook, constantly checking the usage to see if the user has gone over their usage. If they have, we'll kill the job. And an end job hook to delete that temporary folder when they're done. A couple of issues with this approach at the moment. The automatic cleanup can fail for some reasons. There's a script that takes care of it at the moment, but that's something where we sort of need that, hey, I really need this to run at the end of the job, even if something else has failed. And the periodic hook is not completely accurate, not through any fault of PBS, but due to the fact that users can unlink a file and it won't be counted anymore when you walk that bit of the directory tree. Fortunately, I don't think I've seen anyone doing that, at least not deliberately, so hopefully no one reads this and finds out they can do that. It'll be great. I'm hoping none of the users look at it. So some of our other features is we have hooks implementing node health checks before running a job, as you'd expect. We also do add a resource summary to the end of everyone's job output files. So we tell people in the output file, this is how many hours you use, this is how many CPU hours you use, this is how much memory you use, that sort of thing. We do have the option for people to enable or disable hyperthreading on a compute node if they would like it. We do this simply by turning scheduling on and off for a bunch of CPUs in the Linux kernel, and they essentially can get hyperthreading if they'd like to have it. It is a requirement that you request the entire node for that, for obvious reasons, but we still only charge them for the 16 cores, not for the 32 hyperthreads that they'll get to run. But of those original features we had in ANU PBS that we don't have today, so we don't have the process containments with CPU sets and C groups. PBS 13, I can implement C groups now, I'm told. I'll find out all about that on Thursday. And we'll look into that. And we don't have the full suspend regime scheduling we talked about. So the future, our lessons from the present. We sometimes get slowness in scheduling cycles that's contributed by a number of things. One, the time taken for some of the hooks we used. Some of the hooks call out to the PBS command line tools to get information. That ends up establishing a connection, doing a whole pile of stuff that can really hurt your execution time of that hook. The ordering of the hooks really matters. If something's going to reject the job for some reason, do it as early as possible. Don't do a whole pile of work that you don't need to when it's going to be rejected anyway for some reason. This one is probably the biggest one that we see, is the calculation of the start time for top jobs sometimes takes a very long time. This is usually when we have a job that's requesting extremely rare resources on the machine. So we only have 72 of our high memory nodes. So if someone's requesting a number of those, it can be that the time to calculate the backfill for that can actually take a minute or two to complete. And at times, the server blocks waiting for MOM responses when there's something wrong with a MOM. That's, I believe, fixed in PBS 13. It's amazing what you guys have actually fixed when we tell you about things. So hopefully that one will be fixed when we go to PBS 13 as well. So PBS 13, currently in the early stages of testing PBS Pro 13. So we've literally installed it in the last week or so on our test cluster. So some of the new features that I'm particularly interested in from reading the release notes and not much else, support for C groups. Really want that. I really need to be able to lock jobs to the cores that we've actually allocated to them. This is particularly useful when someone decides to launch a job asking for 16 cores when they only told PBS they're going to use 8, and the OS will happily let them do that and they'll be competing with other jobs. Node health hooks, actual support for that, so we don't have to write a bunch of stuff there, we only need to have the checks. Hook configuration files, I really would love to be able to configure stuff rather than having to put it at the top of the hook in a bunch of config there. And asynchronous scheduling, that should really help sometimes where the scheduler is just waiting for a node to launch something. It can just fire off those requests once it's worked out what it's doing. So our customizations, we'd like to keep enhancing suspend resume support that we're using. So at the moment, we don't have an anti-express queue set up to allow bonus jobs to be preempted by any non-bonus job, but that's something we'd like to look at. Let those jobs be preempted, you're getting bonus time, you'll get over it if you get suspended. We'd like some better ways of targeting suspension. We're looking at ways that we can actually suspend just jobs we want to. And for our allocation management, we'd like to further automate things and some speed enhancements where it's doing calls out to QStat, QAlter, that sort of stuff, rather than calling the API directly. And finally, the future of our cloud environments. So we'd like to integrate with our cloud environments for job submission. The biggest issue there is we actually need support in Munge for multiple realms. So I don't need to give the cloud environment our HPC's key, but that's something that's not available in the standard Munge install. We have our own patch that seems to work, but we need to clean that up before we can publish it. And we also would like to consider opportunistic scheduling of jobs from our Raijin HPC to the cloud. So we need to consider what jobs are suitable to be moved. Number one, single-noded jobs, great targets to get off the expensive HPC into a cloud environment. And also, what cloud environments can we use to do it? Do we use our local OpenStack with Tenjin? Do we use the Australian Federated Nectar Cloud? So that's another OpenStack environment that's supported by the federal government as a research cloud within Australia. We host one of the nodes, so we can use that. Or do we look at the public cloud, your Amazons, your Azures, that sort of thing? Oh, and that's now any questions?
Thank you. Questions?
Stunned into silence.
I know you have them. Is there someone who's further away?
I'm interested in the suspend resume you were doing. So when you suspend in your previous, your own AMU PBS, did you suspend the whole job
Yes, so the entire job would be suspended in essentially the same way as PBS Pro does actually suspend a job. So we did the same thing, send a SIG stop to all the processors, allow them to sit there, get swapped out if more memory was needed. We did have some sort of fudge factors to know how much we could afford to allow get swapped out on a machine and how much we should try and keep memory resident as well.
Okay. And were most of your resumes successful?
Yes, so we did actually have a blacklist of certain software to say this software just can't handle it. Usually licensed software which would decide, I've lost contact with my licensed server, I'm just going to die. So we had a few bits of software that were sort of blacklisted as never suspendable, but 99% of the time it was just fine.
And so we don't use suspend resume except for system-wide suspend.
Yeah.
But we run into problems that PBS doesn't always find all the processes that need to be suspended.
So that's where our use of CPU sets came in as well, and that once you've put a job into a CPU set, you can tell every process that's associated with it.
I like that. Okay.
Excellent. Nice.
I was wondering if you saw any issues with NUMA effects when you suspend and resume the job, because I saw that at some users where basically you move things to swap on 2 sockets and then they move back in on 1 socket and run 3 times as slow.
I don't think we saw significantly bad effects with that. Linux is weird in that to actually transfer stuff between sockets anyway with NUMA, it helpfully uses swap. And doesn't just access it across the QPI link. I don't think we ever saw significant issues with that, simply because usually the first NUMA node that's actually going to use the data is usually the one that it should be pinned to anyway, and it was usually the one that allocated it in the first place.
So on the same subject as suspend resume, there's a lot of interest, obviously. You did customizations on PBS. Did you have to do any customizations on some of the applications themselves to put hooks in there?
We do a lot of work working on optimizing applications for users, usually just assisting them. We don't have that many staff that we can write people's software for them. But we definitely have in the past done patching to any number of system components to provide some kind of better performance or better optimization for what we're doing. So we're happy to help users, but we're not going to write your software for you.
Right. But commercial software, for example, you don't get the luxury of messing with their code, so.
Commercial software, we're usually not much we can do other than help them yell at the vendor.
Okay.
Okay, you're now standing between yourselves and lunch, but any more questions? Something behind me? Okay. One more? Yeah, this is great.
Yeah, so in the case of many short jobs, would you direct them to the Linux cluster, or let's say somebody runs a lot of short jobs on your big machine? How do you handle those?
So there's nothing preventing people from doing it. So LC doesn't exist anymore, unfortunately. We have had the same sort of idea over time of that kind of smallish job, and that's where we're considering pushing jobs off into a cloud environment. Usually, our definition of a small job in that case will be more down to CPUs rather than wall time or anything like that, mainly because most of the single-noded jobs tend to be the sort of jobs that actually use stupidly long wall times. So we see this particularly with some chemistry packages where they can't scale beyond a single node and they will run for 2, 3, 4 weeks. and the users would love us to just add more. But we don't prevent people from doing that. We just try to discourage it through scheduling policies and that sort of thing.
Have you had success with job arrays?
Sorry?
Have you had success with job arrays?
No, not particularly. We limit job arrays to a maximum of 10 subjobs simply because we can't control the individual subjobs, so we can't provide different priority for each job. So it's a nice shortcut for the users, but we can't then manage them particularly well.
Okay.